Well, welcome back to part two of what could be. We're going to try not to make it a three-part series. We're going to try to make it a two-part one on the dot product. So we just finished up an example where we were applying the properties, specifically the distributive property for the dot product. Now we're going to get into the calculation of dot products. You see, this is a little bit different. In the previous example, we were looking at properties. So how do you distribute? How do you associate terms? That has changed the order in which you're applying the dot product. And in this case, we actually want to see or use an algorithm, a procedure for finding the scalar that the dot product produces. Because we understand now that through the example on work that the dot product of two vectors is a scalar. So what I would have you do, you can either go ahead and do this first, or perhaps it might be better to come back at this later on. And well, just to lay this all out there, this here happens to be a fact, okay? And you might be wondering, my goodness, just what exactly is that? Okay, because I thought that the dot product was something else. Okay, so specifically, uh, we had learned that the product or dot product of the two vectors A and B was the magnitude of A multiplied by the magnitude of the vector B, and that's multiplied by the cosine of the angle between the vectors placed tail to tail. Well, what we're here to tell you, I don't know why I'm saying we, because it's just me, unless together we all believe. So we now have an equivalence between these two equations. In fact, what you can see is, okay, that those expressions are equivalent. The big question that everybody should be asking right about now is, well, how is that so? How can you just write that, and what exactly does it mean? Okay, so what you're going to find is that on page 373, okay, I'm not going to go through the proof in this particular lesson. I'd really like you to review this later on. Okay, right now we're just going to focus on the skill itself, and I'll have you go back and look at the reasons why. But on page 373, the solution begins by performing an analysis on that trigonometric definition. And what it does do is it then draws in the idea or the concept of Cartesian vectors. So somehow what's going to happen is the vectors A and B are going to be defined in terms of both a horizontal and a vertical component, if you will, an X and a Y. So it'll be denoted A as A1, A2. Okay, and A1, A2 denote the endpoint for the position vector A. And then B, of course, will be defined as B1, B2. Okay, so have a look at that proof and you'll notice that all of those notations do come up and that they are tied together. So let's have a look at part B to this. Okay, and then by all means, if you want to extend your learning, and I really would encourage you to look at the proof on 373, okay, because it establishes the reason why A dot B is equal to A1 B1 plus A2 B2. So let's put this particular rule into play, and let's look at a concrete example where we're given three vectors A, B, and C, and we're being asked to determine what A dot B plus C happens to be. Okay, and with these vector operations, there is an order of operation as well, and what we'll do is we'll first tackle the parentheses. So I'm going to copy down the coordinates for the vector a, and we have 2 comma minus 4. So in Cartesian notation with the square brackets, so 2 comma minus 4 dot and b plus c. So I'll write down both vectors and we'll add more lines as we need them. So here we have minus 5, 0 and plus 3, 6. So according to the order of operations, let's complete what we can see here in parentheses. So I'm just going to change colors here to emphasize the step that I'm working on. And remember, through the vector addition of Cartesian vectors, we would have minus 5 plus 3 and 0 plus 6 as the other coordinate for that endpoint. In the future, it's not necessary to add so many steps. Okay, next line. We'll change colors for the next line. Just to emphasize where we are. So step 3, of course, is then to simplify what we have here. So we'd have negative 2 and 6 as vector b plus c. Maintaining excellent communication, so line to line. And our mathematical work. Let's finish this off now. What we're going to do is apply this definition that was given above. And let's see, I have it in different pieces here. There we go. Actually, let's clone that, so in case I need to have another copy of that. So we're going to bring that down here. And what we're going to do, I'm just going to put this off to the side. And just in parentheses, this will be our reasoning or rationale for our next move. So let's have a look here and see. What we're going to do is we're going to denote this. If this is the vector A, then this would be A1, and this, of course, would be A2. And the other vector that we have, B plus C, okay, that's going to be somewhat representative of our vector b in the general definition. So in this case, I'm kind of reluctant to use the letter b as it's here, but if we want to denote that as some other vector, call it d, okay, where we're calculating a dot d. So in this case, if this is d, then this will be d1 and this d2. So let's call this D1 and this one D2. Now we won't do this in all solutions, but just now until we get things organized. Okay, because there's a specific order in which we apply the operations. So as you can see, we're going to calculate A1 D1 to begin with. So we're going to have 2, and that gets multiplied by minus 2. And to that, we're going to add, right? So adding on the product of minus 4 and positive 6. And this is good because the dot product produces a scalar. And that's what we have here, are 2 scalars that will be added together. So minus 4 and minus 24, giving us a total scalar value of minus 28. Okay, so things that we can draw from this, if you want to think about it, the angle, okay, so if the angle, so if theta is the angle between A and D, and we understand that D is the vector B plus C, then we know that theta in this case is going to be greater than 90 degrees, right? Based on what we had learned in class. So the angle between A and D is obtuse, okay, given the dot product is negative, right? Since A dot D is a negative value. So those are just little things to keep in mind as well. Vector products produce scalars. dot product produces a scalar, and then of course we can assess the angle between the two given the product that we have. Well, let's move on. Let's have a look at this one here. Okay, so what I might do is insert a new page so that things are not getting incredibly cluttered, yet at the same time all of our coordinates are here on this page. So it would be better for me to clone this page right now and then take the cloned page and just clear the ink that's on it. And then we'll start over again, okay, with this one here. So part 2. Let's just go down here, over here for part 2. Now with part 2, what you want to realize is that we don't always have to do everything so directly. So we're at 10 minutes of filming. Let's try to wrap this up in a couple. So I want you to take hold of some opportunities here. Notice that we have the vector b as a part of both dot products. What that means is that there's a great likelihood and a correct likelihood, 100% probability that the distributive property can be used. And just to emphasize that possibility, if we were to take the commutative property and just reorganize the vector dot products, what you'll notice is that the vector b, okay, could be distributed over a plus c. Okay, why do that? Well, I think it's going to really simplify our work. It's entirely up to you whether you want to go that route or not. Okay, so we're going to come back and use this definition in just a moment. But prior to that, what we want to do is to calculate a plus c. So I'm just going to highlight that up here right now. So a plus c, we're really looking at adding the 2 and the 3. So there's a 5. Followed by, again, we're adding a and c. So let's take the minus 4 and the 6. We'll add those together to give us a total of 2. Vector b above, minus 5, 0. And let's go ahead and calculate the dot product, which we know will produce a scalar. So applying this definition here, let's move ahead, and we're going to take the first element of each of the vectors and we're going to multiply them together. So minus 5 by 5. Okay, just going to highlight those so that it's clear as to what we're doing. Okay, and to that we're going to add on to complete this scalar product. That's also another name for the dot product, is the scalar product. Is to multiply the 0 by the 2. Let's see what's going to work well here for coloration without blocking it out. Let's go with a blue. Okay, so there, by completing the scalar product, we'll have minus 25 plus 0, so minus 25. Again, from that you can tell that the angle between the vectors, in this case, the vector b, and as well as the vector a plus c, is going to be obtuse. And that's another great thing too, is when you recognize that you can rewrite this, I think it would be far easier to sketch a diagram to this one here. Right? Because really, you're talking about two vectors arranged tail to tail. One is a plus c, so perhaps we could denote that as some other vector, a resultant, call it d, and then vector b. Whereas above, the question is, how would you represent that in one diagram? And what would the relationship be between A, B, and C? So I think this really does clarify it by using the distributive property. Okay, so given our time, we are up to 15. So we're going to stop this video here. There actually is one more, which hopefully will be only a fraction of time, less than 10 minutes. I'll try to hit 5 if possible.